All right, class, let's go with it here. Let's go finish off the trig function idea that we had last time. You guys have to help me out just a bit. Is what were we doing?
Limit as x.
And what problem was it? And what?
7D.
7D. Thank you.
We did.
It's 7D, but then.
Yeah, we didn't do 7D.
Oh my God.
All right.
How dare you?
Well, D is obviously not part of
I'm going to go to this one right here. So hopefully my notes are here still.
I think they're equations too.
We could just not do C.
We could. That is the thing we can do.
One small problem, that one over there? Yeah, we'll get. Okay, so let's go with D first.
I can do that.
And we'll have to come back to C. It's important. Even though it doesn't have cosine in it, it's still important. All right, this one, what do we say? We say we're going to do it by table, is that right? No? Should we do it by graph?
Yes.
Graph is a lot better.
Because I can do it.
Let's go by graph then. So tell me what the graph looks like. I actually forgot myself here. We're trying to get to 0, is that right? Now, first of all, do we have a little problem here? Yes, it says we have a problem here because you can't have a 0 in the bottom of a fraction. That was the whole point of limits, right? We're not looking at what happens at that point, right? As you get closer to 1.1 point. Okay, what does a graph of that look like?
It looks like.
Make sure we're in radian measurement so we don't do the same mistake we did last time.
It looks like a line with a hole in the middle.
Oh, mine.
Wait.
Okay, let's see what else.
Okay, I can't tell if it's a curve or a straight line.
Mine is like a straight line.
Calculator zoom.
What's a curve if you zoom it right?
Line
Zoom
with a
out.
hole in the middle.
Yeah, Eli, it's just like very slight.
Yeah, it's a curve.
It's a very slight coast, like tiny.
Okay, you guys are
Zoom in.
Are we
It's
zoomed in
not
like
a
crazy in
line.
our graphs? Is that why? You zoom out even more.
No, I'm zoomed out like super far, and it's just a straight line.
No, it's your zoomed up too far. Zoom in.
You gotta
like
zoom
No,
in.
but I
negative-
zoomed in. And didn't
Negative
do
5 by.
You
It
gotta
is-
zoom into like 0.23
Oh, wait.
Gotcha.
Wait, what?
No, I can do it on negative. If I go
or
negative 5.
0.02.
If I go
Oh
between
my
negative
God.
5 and
0.02 for x.
Okay, so how about this here? Eli, real quick on your graph.
Oh,
If
yeah,
you're
then
zooming
you
out
can
like
turn the
this,
brightness up.
Cosine is only going to go up to 1 and negative 1, right? So your y values have to be maybe 2 to negative 2. That'd be easy, and then you can zoom out this way.
My y is 0.23 to negative 0.2.
Oh wow, even smaller.
And
Okay.
it looks pretty
But
small.
wait, are you sure you're doing the right one? Because I have my
Yeah,
y
that's-
is
that's
0.23. I have negative 6. I have like
Yeah,
0.15, and it's
you're
No, I'm
still.
not. I did f of x 1 minus cosine of x over x.
It still looks the exact same.
What do you think?
A straight line with a hole in the middle.
Oh, there, now I can, if I go between, wait,
Are you sure?
I had the curve, and then I went out, so I
No.
zoom way on the x, and then it's between 2. Now I see like the
Mine doesn't do
If I
that.
go-
see that.
So
But
when
I
go,
believe you.
I don't, if I go negative.
Pull calculator.
Ah.
Okay, I'm going.
Aha,
so
the
close.
answer.
That's what I had before, so why did the.
Behold.
Zoom way out?
Okay, I'm at like 2.9 e to the negative 7.
Yeah,
No
it's,
cosine.
it still doesn't do it.
It's still lying.
You gotta zoom in a lot.
No, I'm like at e to the
Dude, I
negative
think
7.
your calculator's
Yeah.
the only one that can do this.
What? Well, it's kind of like it wiggles in the middle and then it starts not.
Negative 10 is 10.
Wait, first, so what do you have, like, oh, not that.
No. Since when?
Man,
How?
your calculator makes it bad.
Wait,
It's still a straight line. I can do it, your A's can do it.
And then-
Okay, are we good with the graph? The graph should look
No.
like.
Do the box zoom
Wait,
and
that's
then just
so
make the
weird.
box like really small.
I mean, your window said he's.
Okay, doing okay?
Yeah.
Okay, tell me if you guys agree something looks like this.
I mean,
what-
depending
I don't know
on
what
the
it's.
scale.
Are you
That's
in
what-
degree
depending on the
still?
scale.
Yeah.
You're supposed to be radiant.
Oh,
Supposed to
okay.
never switch it back from.
Wait, I'm in degrees though.
Yeah, you're supposed to be right.
But I'm in degrees and I get the curve.
That's because
Wait a minute,
calculator
why does
like
mine
this, like,
have a line now? What is
so
this?
powerful.
Oh, I'm so zoomed in, it's a line, no.
Wait,
What?
change.
I don't understand how you're so zoomed into one.
Yeah, mine.
I
it's a
tried to
vertical
zoom
line.
out and it just gave me an error. It's like, no, I'm too zoomed in.
All right, let's go with it because we just have to see
Oh,
this.
oh, whoa, okay, okay, there.
Okay.
That's what happens when I graph it in radians.
Yeah, I don't think you're supposed to graph it in
You're,
radians.
wait,
Ah.
Yeah, when I graph it in radians, I get a straight line that's
Let me
vertical.
zoom
when I
out.
graph in radians,
There
I
we
get the
go.
picture that you put on the board.
Let me
They
zoom
get a
out.
vertical line and then graph it.
Yeah, yeah, I
Are you
have
guys,
like,
did you do the wrong parentheses or something?
Okay.
no. I have
Wait, Eli, what are you doing?
In
just
radians,
zoom
it
out.
gets-
Set it to 10.
It, like-
If it's in radians, just set.
Kate's just
the,
waiting for you
next
guys.
to
Come on,
negative
guys.
10, 'cause
Let's
it's
go.
It
vertical
like,
line.
it like just goes down and
No
like.
matter what I set it to, it's not gonna be right.
Look.
Okay.
You must zoom too, you must zoom too far out, like zoom in on the X.
No, I'm zoomed really in. The X is 0.002.
What?
I am not zoomed.
Well, now we know what the hole is.
What, are you using the wrong graph?
No, this is the right one.
Yeah, I have a vertical line at the.
That's
This
why it's cosine X is all.
That's just what happens when I graph in radians.
Your guys'
Just check
calculator is
something.
being smart, so that they're being wrong.
Yeah, what did you
I
say?
know, he put it on in radians on purpose.
What? I know, mine's in radians, and it's doing what I'm trying to do.
What happens when you do it in degrees?
Oh, yeah, put it in degrees, it's fine.
Okay, let's see if we get that graph. Christopher, you got it. Though, right?
I did.
I got that.
Eli, you have
when it was
it.
in degrees.
No.
It doesn't want to do it.
Do I have the right equation?
Yeah, that's what it's supposed to be. Okay,
Okay,
you guys
now
have the same
make sure
calculator,
you're in
so
radians.
Christopher just
Yeah,
has
I
small.
agree.
No, I got it.
Okay.
Right.
Wait, let me switch back to
Yeah,
degrees.
it is, I just had it in.
Okay, look at it. It's
I can't do it in
normal.
degrees, it won't graph.
See?
Did you put it in degrees?
Yeah, it's in degrees.
Why does yours work?
It doesn't look weird. Although,
I
wait,
did
Mr.
Yeah.
Mr. Hanji, my graph, now that I'm super zoomed
Okay,
in,
so
my
let me
graph
see your
kind of
window.
looks
What's your
interesting.
window?
Not as strange as the other one, but it's like.
Okay, let's go negative 10 to 10.
I appreciate that you actually did read.
Thank you, yeah.
He's gotta represent all of purity, he's the only thing that.
No, this is because otherwise it's too big and it's like squishes down.
Not your ears.
Well, my ears are kind of stick out.
Ears are.
A lot better now?
Yeah.
Okay. So I think it's a window issue.
My ears stick out because of my mask.
Okay, how are you doing?
Yeah, well,
Like,
my
you
ears
like
just
flip-
stick out more.
Okay.
My graph looks like this when I zoom in on.
Yes, you have things, yeah, compiled together.
Yeah.
Uh-huh.
There's
It's
so
like
much
I'm modeling a
fun.
ball
I'm
bouncing.
sure. Well,
Uh-huh.
that's my-
That's what trig functions are made for. Okay, guys, rule finally. So I got a few things here. So when Eli graphed his did this, which is supposed to do, he went like this, and then it went like this. It kind of broke that little piece in the middle. Is that right, Eli? Okay. Reason for it is because most likely his calculator, when it was calculating the little points, hit the 0. He actually plugged in the 0. It was not there, so it actually did not graph it. And then the calculator's graphing, let's say this was negative 0.12736. It graphed that one, it found it, but when it graphed 0, it didn't find it, so it didn't connect those pieces together. Then it graphed positive 0.46263, and it started that graph over there. Now, right, the whole point is that little guy right there, right? You can't divide by 0. And so when we have that, we're just looking at limits. We're not looking at what happens at 0. We're looking at this function as it gets closer and closer to 0. And we'll take a look at this function later on because it'll be important. So all yours, go for it. Answer is all that work for this. Da 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 da.
Let me zoom in more.
Yeah, Sadie's correct. It's 0, isn't it? Because the graph, it doesn't go like this, right? It doesn't go in split direction. It's not split in this way, right? It's not split like it's hitting a different spot, right?
That's what mine looks like. I'm just using more than you.
So go back to what we've been doing, right? The final limit is just a calculation. So the calculation goes like this. What happens as it approaches 0 from the left? What happens to it as it approaches 0 from the right? And if those two match, we got ourselves a match over here as well. We're good. Boom, done, done. Okay,
That's with my calculator and now it does not have to do, negative. Oh, there we go.
okay.
I think.
Yeah.
So what is the answer? Or what is 0?
Ah, so 0 is the limit from both directions are converging onto a single point.
Okay.
And because they're converging, we say that limit is that number.
Did not fix it.
Okay, let's go back to C. This is the one that Christopher saw on my graph. And so let's talk about just a few more things here. The book doesn't mention this, so I'm gonna go kind of a little bit beyond it just for a little bit. The graph of this guy, if you're to graph it, let's back up just a little bit here. On this one, on the tables, notice on the tables for example 7b, we did it by table, and we got what we needed, right? It was 0.9983, right? And it switched to a 1, and it was a 1, 1. It was very close to 1. So tables are the way to go. They get us exactly what we want. And once you get close enough, you're great. Good? Maybe. Just maybe it's great. So this one is the one that kind of breaks the rule. You know how Ralph broke the internet? This one breaks the table rule.
So this is Rector Ralph's fault.
Uh-huh.
I'm glad we have another thing to blame.
So if you do this, let's go from, I just want to show it to you here. Let's see, maybe I should graph. Oh yeah, we have it in our textbook, but let's just do the textbook one because it's easier just to show.
Is that probably 44?
Yeah, it's going to be close to what we did for 44.
No,
Yeah,
this is mine.
theta.
I can't remember what the problem was. I just had
For sine of 1.
Uh-huh.
So find your vertical.
Okay, here's where it looks like right here. It's on page 143 of your textbook, and it looks like
Even
this.
Smaller than the other one.
You good?
Yeah, no, this is still mine.
Here's your graph.
I did something wrong.
Of sine of 1 over x.
Uh-huh.
I messed
Let
up.
me switch to let's put the window. I'm just getting that. I need to switch to the.
For radians?
See what happens.
So what we're good there? I don't want you guys to graph it. I do want to point out something. Here's the problem that breaks the whole concept of just plug in values closer and closer and closer to get what you want. Because if you're to plug in 0.1 into this function, actually I should say it's negative 0.1. It gets to, well, it looks like it forms a pattern at first. So let me show you the pattern here and see if you guys agree here. So I do this. I do this. I'm just going to take it from the textbook itself here. So let's go with 1, 2, 3, 3 zeros. 0.305. And I'll stop there here. So
Is that 0.544?
0.544, 0.5. In fact, let me get rid of this one. Let's have this discussion here. I'm going to get rid of this one first. So as you're looking at these two patterns right here, it's pretty close though, isn't it? Would you guys say it's pretty close? It's negative 0.1 and then negative 0.01. What do you think the limit looks like based upon the first two values? I almost want to. I'm gonna say just based on two values, I'm gonna say 0.5 or 1/2. Is that right? Okay, and as we get more and more values into it, it starts to break down. And the reason for it is because you might just hit values with the chart. You might just hit values that are going like this. They're getting more and more condensed in, right? But you're hitting those values that are actually hitting at 1, or you're hitting those values that are hitting a certain pattern. But because it's switching back and forth so fast, you realize a pattern that's really not even there. Are we good? Okay, does that make sense? That's why I want to kind of get you out of that problem there, right there.
No, we should not do tables. It does not work.
Well, apparently my calculator.
Before calculators were invented and graphs were made easily, we had to do tables. Yeah, so part of that. Okay, 2.2. Are we good there with that?
It'd be interesting when there are supercomputers and calculators.
Mm-hmm.
It's like, oh yeah, what is I, and it actually is
The other piece, because I want to start the next one pretty soon here. Okay, we got that one taken care of. And then the book doesn't mention, but we do think about things that go to infinity. And so limits, let me just kind of quickly just hint at that and we'll go from there. Limits to infinity. Or limits, yeah. No, it's, and what you really are looking for, you're looking for what's the function doing when it heads out all the way that direction. And we've seen it before. I think the book doesn't mention it because you've seen it in Algebra 2. It was called whether you have horizontal asymptotes or not. Right? Because if you're just going off to different directions, you're just looking at this one and you're looking at this way, right? You're looking at what happens at the ends. Right, we've looked at what happens at the ends with, just real quick here, power functions. You guys remember power functions here? It was like this. It was like x squared.
Yeah.
X squared isn't a power function. You guys remember from Algebra 2? Just real quick, I'm kind of slightly rambling just to make sure we put a few pieces together. If I have this right here, like that is my function, right? You guys remember in Algebra 2, it says, what power function does this closely resemble? And you would just take your leading term and you say, oh, that's the one right there, because whatever happens in the middle right here, I know whatever happens here, it's still going to come up and it's still going to go to that function there. We're good? So power functions allowed you to see what happens at the ends. We're good? And then horizontal asymptotes were the other stuff that used to happen here. So if you had something that looks like this, a function, I think you guys remember these kind of functions. You guys remember those kind of functions like this? Rational functions, maybe from Algebra 1 even. You'd say that.
No, we didn't have one. We didn't have.
Okay, so this function, it's a rational function. In fact, we could probably even, I can write, let's say this is 3, negative 3 here. This would be x plus 3. And this would be like x plus 1 or something. So horizontal functions, you would take the two leading terms, right? Because it's just a ratio. You'd divide out the leading terms and voila. Oh, it should have been like this. Right there. Okay, are we good there? You can turn those into limits by saying this. Okay, this piece right here, what's the limit as that function? I'll call it f of x.
Oh, I know what you're talking about. That's where like it gets really big, so the +1 and +3 don't matter anymore.
Uh-huh.
I get what you're talking about.
X goes to infinity, sorry. X goes to infinity of this function here. So you guys talk to me here. What happens, what is the answer here? As x gets humongous. Answer is? It's not infinity. 2. Are you good with 2?
If you divide the x's and then you're just not supposed to.
That's what's happening at the end right over here, right? Does it approach some kind of limit? So limits at infinity and negative infinity are really just horizontal asymptotes. That's what they are. And you've studied them before, and that's a 2 right there. Okay, we're good there? So we've seen limits in a conceptual sense. Okay. I think that's enough information for us to start with things there.
Now is it 2.3?
Now 2.3, let's see if we can finish it up here. Oh, hold on, we got the homework question, right, Sadie?
Oh, I mean, it's fine. It's just at like 77 and 79. Kind of was just weird, but I just wanted to make sure if I look at the limits and I just kind of make figure out sort of like what the limits look like, because that answers me barely.
Yeah, because you can make all sorts of different graphs as long as those conditions are met. Let's just do it real quick.
really want to, but.
Okay, let's just do it real quick here. Let's do 77.
79 is here.
77,
That's
yeah.
also longer though. But yeah, 75, 75.
Which one do you want?
I don't care.
Okay, I'm gonna go 77. And let's get suffer with 77, 79. So here it is. I want to create a function that says this. And if you have your textbooks here, here's what it says. It says the limit as x goes to negative infinity is 0. As it goes to limit as x goes to -1 from the left-hand side is negative infinity. From the plus-hand side, it's positive infinity.
What?
Ah,
Are you doing something?
I think I'm doing 77.
F of x is equal to, what is that number, 2?
Okay,
And then.
talk to me here. This is 77, this is 2.2.
Oh, yeah, no, this is not even, okay.
And let me go this way here. Christopher, you ready? X goes to
It's like
-1
you
from the
just
left-hand
make the
side.
graph based on knowing that where the limit goes.
Let me just write it out here, just so we
Like,
have it
when,
here.
when you know that y is 0, then x is going to -50, you just kind of like drop it. Which is kind of weird.
Let me rewrite the problem, not with my chicken scratch.
77 from 2.2.
Okay. Okay.
Is 1, and limit as x goes to infinity.
A, B, and
Wait, those aren't the more problems, like the.
Okay, 77. That took a while just to write it down. It's on page 158. 158, So real quick here, let's see what we need. We need the limit
Oh,
as x goes to negative infinity, it needed to be 0. As it approaches -1 from the left-hand side, we need it to be negative infinity. Approaches from the right-hand side, we need it to be positive infinity. That's probably the easiest one to do. As it approaches 0, it's actually f of 0, and f of 0 is actually 1. As it approaches positive infinity, it's negative infinity. Okay, let's do the easy one first. These ones will all be different. You guys will not have the same graph because you're forming your own graph.
if we do it in classes, you know.
This is probably the easiest one because it already tells you which way you're going. So as it approaches -1,
It's a different graph for each one of these.
no, it's the same graph incorporating all these pieces.
Yeah.
So what do you guys know? As it approaches from the left-hand side to -1, it goes down to negative infinity. As it approaches from the positive side, it goes up to positive infinity. What is that?
Well, it's like you have a fraction.
Starts with an asymptote and it ends in tope. Asymptote, all right. There it is. So we have asymptote of -1.
Is it asymptote or asymptote?
Asymptote. There's a little m in there.
And so, you know,
So it approaches from the left-hand side, it goes down this way. So I got at least this piece here. We're good? That's what's happening there. And I got at least that's what's happening there. Okay, are we good there with that one? Done. Check. Next is this whole concept of going off to negative infinity and positive infinity. And so let's handle this one. It goes off to negative infinity. The answer is 0. So it has to be
Horizontal asymptote.
perfect. Yeah, horizontal asymptote as it curves this way. Perfecto. And then all the way down here, right? Because now we want to do this one here, right? Somehow it's going to go off to negative infinity. So somewhere over here, it's going to go this way. Are we good there? Now, it doesn't have to be going that fast, right? It could be just going straight line because that goes to negative infinity too, right? It actually could be a slightly curving up line like this, but still going off to infinity, right? There's a whole bunch of ways to go to infinity. Okay, and then these piece here. This is the more complicated one right here. So if as x approaches 0, f of x, the function is actually at 0. So that's the little thing called continuity, which means the point itself is going to be the limit itself. So notice that guy corresponds to here. So the function at 1 actually goes through 1, and the limit is 1. So if you go like this, it has to hit this point somehow. Doesn't tell us when it hits the 0 marker, so that's fine. Goes like that, or you can even change it up to go like this. Is that okay? Okay, talk to me.
Doesn't matter how you draw it.
Doesn't matter how to draw. That's why it says answers vary. So if you guys want us to take a look at number 79, that's fine too. Sometime.
It's just the same.
Yeah, but it's the same concept.
Quality and then
Okay, are we good there?
it's just like the graph doesn't make doesn't look like it should.
Can we actually craft that? Like, what kind of-
Do it on
Well, you
Desmond.
just
How
have
would
a
you do
function.
that? Do it on Desmond.
I don't, is there some function that would have all those things?
That could be so many functions.
No, because you're putting
All of this.
you're putting something together based upon,
Is there an f of x that would work in all of those cases?
yeah, you have to find it though, yeah, but you can make it work, yeah.
How would you find that?
Easiest way to do it is do a piecewise function. So at this point, up to this point you do this, up to this point you do this, and that way you do this, but then make sure they connect together. Next is, that's a rational function. It's a pretty easy rational function to draw. This one would have to be a rational function that, because of this happening here, usually rational functions are going to happen, right? Usually the endpoints are the same for rational functions.
Yeah.
So then at that point, yeah, it's going to be piecewise function, cut it off somewhere, and then do the rest of it. I'll probably cut it off right here, cut it off there, and then do another function after 0. Okay, are we good now? All right, 35 minutes to go. Let's see what we can do. Thought I was going to get through 3.2.
You can finish 2.6, you just heard.
Okay. We should take our time though. I'd rather do that than hurry through something and not understand. Okay, 2.3, here we go. The limit laws. Ooh, some laws here. Okay, so let's backtrack just a little bit just to make sure we got it. So do you guys remember the two basic laws we have already? The properties, two of them. Roman numeral 1.
Then x is x goes to a equals a.
Perfect. So if it's a constant function of c or of a, limit of x. Talk to me later. Was it x or
Yeah,
c over here? X, okay. That gets you a. Cool. And then the second one. Okay, limit is, I think it's written like this. Tell me if you, right? Yeah, limit is if you have a constant function, if the answer is f of x is 5, you know the limit's gonna be 5, no matter where it goes. Okay, let's develop some other laws here as we go. I'll write them down in just a little bit here, but first let's do an example problem first here. So I have this little guy here. You guys tell me quick little limits here. Example, because we're not solving it. This is just to get us to the example. Example 1. I'm not sure if there'll be example 2, but example 1 is this. Yeah, there should be example 2 here because we're going to connect it here. I got f of x. Let's do some easy ones here. F of x is equal to x squared. Good there? And I need to know the limit. As, write it on the bottom here. I need to know the limit of f of x as x approaches 3. That'll be easy enough. All yours. Answer is pretty easy. 9 is okay by me. Everybody agreed with 9? Awesome. Okay, Taya, tell me, did you watch the video from the other class? Okay, so you ask as many questions as you like. We're good? Okay, you get to ask questions. So as we go out to 1, 2, 3, we're saying as x approaches 3, our function, what's the y value that it approaches? It approaches 9. And it does it from one side, does it from the other, and we notice it's continuous. That's cool. Okay, so how about this? Limit as x approaches 3 of this function now. It's 3.
Like, what's the point of limits?
Oh, we'll get to those. We're still just starting.
It's like almost getting there with.
We're just starting.
Oh, boy.
We have a whole 3 weeks in this. Okay, example 3. Let's put it together. You guys tell me, what is the limit? I wish I had it on on a chalkboard or something here. Example 3 is this. I'm going to give you a function. The function is going to be this. I need to know what is the limit as x approaches 3 of this function. Again, 12. Everybody agree with 12? Everybody agree? 12, 12? Yes, I agree. Because when we graph this function, is it going to go like this, right? It kind of goes like this, and then it goes up like that, if you guys want to graph it even. 1, 2, 3. But we notice interesting something about limits is the fact I can break this up into these different pieces. So notice that's 12, and I think we could do this here. This is cool. How about this? If I do it like this, talk to me. Tell me if you agree. I can do this. Limit as x goes to 3 of x squared plus the limit as x goes to 3 of x.
Oh, yeah.
So that'd be 9 plus 2.
So the limit, oh, awesome. Love it. Okay. So limits could be added.
Oh.
And if limits could be added, they could be subtracted.
Oh.
They could be multiplied. Absolutely. Multiply.
Division is gonna
No.
So what else can we do with numbers? We can take powers of them, and we can take roots of them. Love it. There's my.
No.
Logarithms and
Can we take a logarithm of a limit?
We can take a limit. We can limit of a logarithm. Yeah. Okay. Here it is. Real quick here. Do we need to write them down, or do you guys say? Should we write them down?
Sorry, what that?
Or it's on page 161 in your textbook. If you have your textbook with
What
you
is
here,
log or?
it's just gonna take a long time to write them down.
Yeah, it's not easy.
Okay.
I can turn out that page.
Limit as x goes to a of f of x plus g of x. I guess.
Like PEMDAS of
It's not without that big,
PEMDAS of limits.
Yeah, no, but it's not that, it's not an order of operations.
Oh, but I don't want to write addition, subtraction, multiplication, division, blah, blah, blah.
Let him be wrong.
That's A down there.
A,
Oh, right.
That's a G. Should be a G. Change things up here. Okay. Addition. Subtraction. Yeah, you can combine them, absolutely. All right, limit as x goes to a of something that's multiplying f of x is the same thing as limit as x goes to a, oh, sorry, c goes in front, now multiplies this whole thing. So constants I can take out. Multiply by 3, like that x squared that we had just now, right? If it was 6 times x squared, I could just multiply the 6 at the end.
So C stands for
It's
constant.
like logarithms,
Constant, yeah.
right? Or, but it's an X.
Uh-huh.
It's sort of similar.
So yeah, it's a multiplier.
So
It's
what
a
if-
product. Good.
X goes to A is not the same. Can you subtract limits that don't have the same?
Ah, good. No, it has to have a has to be there. The limit has to go to the same exact number. Okay, so that's a constant
Is there a way
multiplier.
to like change those like logarithms so they work together to subtract?
No, you can do them individually, but then it won't make sense. Why would you look at a function going to 2 different spots? It would not make sense. Okay, are we good there? Adding, subtracting, and a constant multiplier. Tell me if you guys are done. Tell me if you need more time. Good. Okay. 1, 2, 3. Next. The product rule. 2 two functions multiplying each other. Split them off into two different pieces and take the limit of each one individually and then multiply them at the end. Oh,
Your application is not responding.
too much for PowerPoint.
Oh,
Oh, okay, it got feisty. Boom. Okay, quotient rule. Quotient rule is limit as x goes to a, and then we've got a division on our hands. That just means I can split it off into limit as x goes to a of the top, limit as x goes to a of the bottom, and I got my answer. The power rule, and we're almost done here. Power rule says if I have a power that's being put on my function, I can take the limit of the function first, and then take the power of it. And then same thing happens with roots. I have nth root. I guess we should clarify here. N has to be a positive integer for that to take place. And then the nth root, limit as x goes to a of f of x. Okay, and then remember with roots from algebra 1, algebra 2, roots are kind of funny. If you have a, right, you can't have a negative inside a even root, right?
You should just not have negatives inside your root.
You can have it. You can have it said odd roots. Yes. Uh-huh.
Because it's,
Oh.
is
So
that
then-
second exponent H?
Still uses
This one here? Oh no, it should be n and n. N and n.
Okay, no.
Uh-huh. So the disclaimer is n is odd. There's no condition. Done. If n is even, then we just have a condition that f of x has to be greater than or equal to 0. Right? It's only for positives, so only work for positives. Okay. Yep, I think we can do it. Okay. So let's go with it again. Tell me if I'm going too fast. I can come back to the page itself. This is interesting here. Good. It's just the beginning of the algebra stuff, and then we're going to learn techniques as well after this here. So now let's get to some exercise problems here. So we just start off. Let's start off easy. Limit as x goes to 2 of
Are we breaking this up into like separate parts, like for the other one?
Yeah, so here it is. So if you're going to do this properly mathematical way of doing it, you would split off the quotient, right? And then as you split off the quotient, then you would split off each of the pieces themselves, right? And then work the individual pieces themselves. Now, that is the proper math way of doing it. Do we do that? Heck no. It is much easier just to plug in the 2 if you can, plug in the 2 and you're done. But knowing that all those properties are in the work in that process, right? Does that make sense, guys?
Yeah.
Say, does that make sense? Because you look at me kind of funny here. So,
So in this case, it's just one and two, right?
yeah, so,
Pretty easy to do.
just plug in the 2, that's it. the proper math way of doing it, you would go to here, then you would split. Because of the addition and subtraction rules, right? And then I'll just show it to you, but you guys, you just plug it in the 2. And then this gets tiresome as well to write all the limit as x goes to 2. So then some textbooks, they just say, forget you, I'm gonna just. I'm not even gonna mention the limit. So they don't even mention the limit there. Limit as x goes to 2 of 5, and then, okay, then you got the constant, remember the constant rules that we're talking about? You got all those rules, but what does the answer go? And I didn't even know the answer, because I'm just coming up with this in my brain here, okay?
Yeah, over negative, yeah.
Okay, 14 is good? Oh, so negative 14 is the answer, right? 14 on top, negative 1 on the bottom, done. Okay, that's easy enough. So now let the fun begin. We good? So if you can plug it in, absolutely plug it in. Good.
Yeah.
So then what happens if you can't plug it in? And that's where we have fun.
Is there a limit function on our calculator?
Ooh, there should be. There should be.
I mean, there should be.
Let me look in the big.
Well, Enrique probably knows.
Yeah,
Let me
but
scroll
I mean, it seems like
up.
such a big part of math. It should be in
I
our
don't see
calculator.
one. Not in math.
Well, it's not in math, but we have
Wow.
so many other buttons.
I guess I should say this.
Stat. Want to do the stat?
Oh, I am.
Equality in an equal intersection, minimum intersect, fx dx.
Let the fun begin. Techniques in evaluating limits.
I don't think my calculator has one, or if it does, it's abbreviated string.
All right, maybe let's see. All right, so first question is this: can we plug it in?
Yes.
It's gonna be yeah, the little problem with fractions. Here it is. We're gonna get a 0 on the bottom of our fraction, and it is not possible to just plug in like we did last time. Dale?
So in all of these problems, are you plugging in the limits as arrow 1, 1 would be plugged into the x?
Yes, except for number 1, it worked just fine.
Yeah.
Number 2, it's not gonna work because as I plug in a 1 into my denominator, especially with rational functions. So let's go back to see our problems. Our problems with functions in general from algebra is the fact that when is the only time you have issues with domain? If you just had a linear function, is there any issues? No. Polynomial functions, are there any issues with domain and range polynomial functions?
Darn fraction.
It's the darn fraction, that's the problem. It's these guys right here. It's that little piece there that destroys it. For square roots, for that one, it's just you have to have 0 or greater, right? So there's no graph in the first place, right? But for these ones, we're gonna have to deal with a lot with these pieces right here. And square roots a little bit, third side fractions. Okay, so what do? I think what we do is we start canceling stuff off. Let's do this here. Can I do this? Can I factor x squared minus 1? X plus 1, x minus 1, and then an x minus 1. Oh yeah, I like this. What can I cancel? X minus 1s are gone. I'm left with x plus 1. And if I can factor and cancel out that little guy, I got myself a 2. Everybody agree? So this is the factor and cancel technique. All right. And just real quick here, let's see this. If you guys can, hop onto your calculators real quick here. Can you graph this for me? After you're done. So x squared minus 1 divided by x minus 1.
Zoomed in, let's see how massive this function is.
So maybe go out like 5 by 5 window or 10 by 10 window, right? But -5 to +5, -5 to +5. Graph that. Does it look like an x squared function?
Hold on.
It does not.
It's a straight line.
It's a straight line. What's going on? So hold on. So x plus 1 is my function. And then I have my other function called g of x. If my function is x squared minus 1 over x minus 1. So what's the difference between x plus 1 and x squared minus 1 over x minus 1? What is the only number I can't plug into g that I still can't plug into f? 1. Okay, so this function here on a calculator looks exactly the same, and it is. Over here looks exactly the same, except when you get to 1. At 1, oh, we have that little dot. Are we good? That's the dot that we just got rid of.
Yeah, it doesn't look like there's a limit function on our calculator, which is sad.
Okay, are we good there?
Unless there's some Greek number instead of lim.
No. All right. Christopher's day just became very gloomy. He couldn't find how to use his own calculator.
What LIN? What happened to that?
LIN?
Well, like watch this stuff. LIN.
I have LCM. I have no idea
That's
what
least common multiplier.
All right.
All right, we're good. So we got one technique done. It is the factor and cancel technique. Next, what happens if we get stuck on something like this? Let's see, that was, this is 3. All yours for this one here. Limit as x goes to 5. Still a fraction, obviously.
Oh.
Do you think we can factor that guy down? No, I don't think so.
That is.
Huh. Okay. You see, if we square it, the problem with squaring it, you're still gonna have the x minus 5 in there, yeah. Yep, I can sing Jeopardy. Da, 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 da. I don't know. What do you guys know? Any techniques from algebra that you guys think of that had to deal with square roots, had to deal with them being in a fraction, had to deal with rationalizing one or the other?
Multiply the top and bottom by the square root of x minus 1.
Almost there, almost there. I'm going to start it here. Multiply top and bottom by a square root minus 1 plus 2. There we go.
Oh,
Do you guys remember?
Right, because then you get x minus 1 squared minus 4.
Yes. Okay. Does it work all the time? No. It only works in very specific pieces, which is right here. Multiply by the conjugate. So multiply by, you guys remember conjugate from algebra? Conjugate. Okay, let's see how this works. So technically we're multiplying in a constant, is that right? That constant is 1, but that 1 is very specific to what we want here. So let's see what we got here. Do you notice that it's still a cancellation technique though?
Yeah.
Right? So as you multiply into here and here and here, what do you guys say on top? I just want to make sure this is x minus 1, is that right? The middle terms are going to cancel each other, is that right? And then negative 2 plus 2 is going to be minus 4. This is x minus 5 on the bottom, multiplied by a x minus 1 plus 2, which gives us the limit as x goes to 5 of x minus 5 on top, x minus 5 on the bottom. That's exactly what we've been waiting for. We've been waiting for that guy to go away. And it has gone away, right there. Limit as x goes to 5 of 1 over the square root of x minus 1 plus 2 this time, and give me the answer if you can.
One over the square root of x minus 1 plus 2.
I think we're going to 5, right? Limit is going to 5.
Yeah.
5 minus 1 is 4. Square root of 4 is 2. I could write it over here. Square root of 4 plus 4, and 2 plus 2, and voila. 1/4.
Was there one on the top?
Oh yeah. With numerators, whenever you cancel a numerator, you always have to have a 1 because you flatten it down to a unit fraction. If you have 1s left on the bottom, you've flattened it down to a whole number, and you don't need that. So on the bottom of fractions, you don't need 1s. Top of the fractions, you desperately need one piece of something. Okay, one more we gotta get to. So this is called the multiply by conjugate and cancel technique. We good?
I see where that only works with very
Sorry, couldn't hear you because of the bus.
I was just saying, I see where that only works in very specific circumstances.
Very specific, yes. Okay. Next one. We got to get through this one at least. Exercise 4. So how about this here? Limit as x goes to 1. Oh yeah, you guys are gonna love this one.
Oh no.
No.
Fractions of fractions is always end up being very screwy.
But can we just, make it into one, the whole thing, multiply by 1 over x minus 1? Does that help?
Yeah, let's see. We could do that. We could just multiply a common denominator, both top and bottom. Would that work too? Yeah, there's two. If from algebra, you guys remember there's 2 techniques to work this out, right? You work it out by simplifying the top as much as you can, and then multiplying through by common denominators. Or you could just multiply through by common denominators. So let's multiply through. So I see a common denominator here is 2, as well as a x plus 1. Is that right? I'm going to multiply that guy here and here. X goes to 1. And let's see, this is going to be the big stuff here. So this goes to here. X plus 1's cancel. I'm left with a 2. As that goes to there, the 2's cancel. I'm left with x plus 1. On the bottom, I'm left with, let's see, x minus 1, a 2, and x plus 1. It can't cancel anything yet because, let's see, this is going to become 2 minus x minus 1. Everybody agree there? Let's keep the denominator still spread out here. Limit as x goes to 1. This is going to be what? Negative x plus 1? able, you guys talk to me here, am I able to factor out a negative on top? Like this. Are we good there? And do we see something that cancels? Done. And did that just get rid of my problem? Yep. And I'm left with a -1 on top this time. I think I'm ready to plug it in. Is that right? I think I'm ready. I got rid of my little x minus 1. Again, is it very specific again? Yes, it is. Say again?
-1/4.
I think so. Everybody okay with -1/4 or 2 plugged into there gets me a -1 on top, and 2 plus, oh, so 1 plus 1 is 2, 2 times 2 is 4. So -1/4 is what I got. Tell me if you guys agree. Yeah, we can do one more here. Okay, next.
So what, is this still the multiplying quantity?
Okay, let's name this guy. What do you guys say? Name it as multiplying through by common denominator, right? Multiplying by common denominator. Okay, and example 5. One more. Let's see if we can get one more in. And this one. Is it 5? Yeah. All right. Limit as x goes to 0 of all right, let's see. I'm going to do the technique. You guys ready? I would just simplify. I'm going to just sort of see if I do this.
Yeah, can you just
I-
make common denominator?
Yeah, I'm going to have to add them together anyways, right? To see what that function is here. So as I do this here, limit as x goes to 0. Common denominator is what? Let me factor this out. This is x and x minus 5. And so common denominator would be x and x minus 5. So for the top one here, no changes to the second fraction. For the top fraction, I'm going to have to multiply through by an x minus 5. Tell me if you guys agree. No change for the top fraction. That's cool. Limit as x goes to 0 of, oh yes, exactly what I wanted out of this. Limit is x. Actually, I can drop my extra parentheses here because it's one term now. X's are gone. That's gone. 1 and 1. Boom. Again, we're getting somewhere, guys. We're getting somewhere. It's just a long process, you know? It's kind of like you're starting to hike on Bishop Peak, right? And we just took the first 10 steps. And you're like, where are we going?
Why are we going there?
We've got to see the pyramid of mathematics. So, good there. I think the answer is -1/5 is good. Okay, so we've got some techniques on our hands. We started the first 10 steps here. We've learned we can plug in stuff. we've learned we can apply these little techniques. And now the question starts is what happens if you just can't cancel? What happens if you can't quite figure it out? So we'll start that. I don't want to give you homework yet, so wait till we finish it off on, is it Monday, right? We'll finish it up on Monday.
So there's no more homework.
No homework for today, because it's in the homework, it's all jumbled up. Now, as I looked at it, because you need to know all of it. Let's see, maybe. Can I, well, let's see, can I, I'm gonna just change it up on you here. Let's see. Direct substitution. No, actually, this one is this one's actually okay. Sorry, class. Now that I'm seeing it here, for some reason I thought it was all jumbled up. Let's start it here. Can we go 83? I don't want to do every single odd. That's like a little bit too much. And I just kind of throw out. That's what I'm going to do. Yeah, just one of each type. You know what? Never mind. Here's what I'm going to do. I'm going to look at it a little more closely because I don't want to just give you guys. I'm going to specifically give you guys certain ones here. So I'll email it to you guys.
Yeah.